Hello everyone. So let's talk about an algorithm, BuildHeap, how to build a heap. In previous discussions, we talked about different operations on a priority queue or heap. We talked about, say, remove element like top element from the heap, adding a new element to the heap. But the question is like in all of those discussions, there was already a heap, right? And we actually operated on it. But how do I build a heap itself? And what is the time complexity? So let's formalize the problem. Say we want to create a build heap operation or build heap routine, which takes like n elements, e1 to en, and we'll build a heap out of it. Okay, so the first, or I think the first intuition that comes into mind is why don't we do like call add operations like n times? We call add e1, then add e2, right? Add e3, up to add en, right? And then the heap is going to be built. Yes, obviously that's a very good, also smart thing. So calling add n times. In that case, what's going to be the runtime? Say, okay, so the runtime is going to be order of log n. The reason is each add operation has that order operation has a runtime of log n. So n add operations is going to be n into log n. So order of n log n, right? Okay. Okay, so technically it's not that bad, but I'm going to explain why. But the question is, can we do even better? Okay, so before I asking that, can we do better? The first question that we want to ask is, why is taking order of n log n? Why is taking so much time? For that, you need to understand the structure of a tree. Okay, so this is, suppose your current heap. As we know, the heap is a complete binary tree. So once you are adding a new element, the new element goes here, right? Okay, so, and after you add, you probably have to bubble up the element. So how many steps you need to work? You need to work like 3 steps, right? Okay, so you see here that all the new nodes that are being added to this new level, right, need to work like 3 steps. So like there are 8 nodes that may need to work 3 steps. If I add more, right? If I add more, they will be added here, right? So in total, and how much work they need to do. Now these nodes need to work like bubble up 4 steps each, right? And how many nodes there can be in total? There can be like 16 nodes. So here is the issue. When you are actually doing calling add n times, we're increasing the height of the tree, and more nodes are actually working more. So more nodes are working more. Next time, if everything is filled up here, then the new nodes here in the new level is going to work 5 steps, right? And there will be like 32 of them. So more nodes working more. That's the issue. So there is a clever algorithm, Floyd's algorithm, that actually works on this idea. How about keep the less work for more nodes and more work for less nodes? So overall total number of operations are going to come down, right? Okay, so the idea is first to dump everything in an array. We know that array can be a smart implementation of a heap, and bubble things down instead of going up until the heap invariant is satisfied. Let's give you an example that will actually help you a lot. Okay, and the idea is like most of the nodes will do just a little bit of work. That's the idea. Keep that in mind. So this is your input. Someone asks you to build a heap out of it. First thing we do is we dump everything in an array. Let's do that. So let's dump everything in the array. Just dump it blindly from 12 to this. Okay. So once you dump something in an array, you know that using the indices of the array, we can make a parent-child relationship. So virtually, this array is holding a complete binary tree, which looks like this, right? Okay, so the structure invariant is satisfied. But the problem is, I have just dumped things blindly. So the heap invariant is by getting violated, right? We have to fix this. So there are two things to notice here. First of all, what we want to do is we want to just fix from top to down. And we want to start at the bottom level. Okay, so we know that the top level has like 2 to the power 0, 1 nodes, 2 to the power 1, 2 nodes. This is 2 to the power 2, 4 nodes, right? This one will max have like 2 to the power 3, 8 nodes. That means we know that this is level 1, this is level 2, this is level 3, and the rest is level 4. From the indices we know. Okay, so let's start. And also we know that like if the tree has n nodes, n over 2 nodes are here, n over say 4 nodes are here in this level, right? So most of the nodes are in the bottom level. Anyways, we will start at the bottom level. So the bottom level, the last node is 6, and the first node of the bottom level is this one, 4. And we will try to bubble all of them down. Now you see there is nothing in the bottom after this. So there is nothing to be bubbled down. So that means we are done. Green means these nodes have no issues. We are done. So let's move to the next level, level 3. Now level 3, you see that 9 and 2, they are fine. 9 has nothing, no children, so no bubble down. 2 has a child, but it's bigger. So 2 is fine. Next, we move to 10. Now 10 has a child that is smaller than 10. That was 7. So we make a swap. Okay, so we make a swap between 10 and 7. Okay, so next we move to 3. Now you see 3 is fine. 3 has no issues, so we're done with level 3. Next, we move to level 2. Okay, 3 was fine. So next we move to level 2. 11 is swapped with 2, and then 11 is okay, 11 is swapped with 2, and next I have to keep on just fixing it until like I have to do the bubble down thing until the whole invariant is satisfied. So 11 is next compared to 6, and there's a swap again. So 11 from here, it came all the way down to here. Okay. What about 5? Now you see 5 is going to come all the way down to like from here, it will come all the way down to 4. Let's look at this. Okay, 11 and 6 is done. Okay, now let's look at 5. 5 is swapped with 3 and 5 will again be swapped with 4. Okay. So now it's level 1. In level 1, you will see 12 is going to be swapped with the smallest child, that is 2. Okay, and then it's going to be swapped with 6. And then it's going to be swapped with 11, right? So first swap. And finally, 12 comes in its own position. And this heap is a perfect heap now. Okay, so how much work we did? You see most of the nodes here, like these level had most nodes. These nodes had done nothing. These nodes, n over 4 nodes, just did one step of work, right? The nodes that were here, they did 2 steps of work. In the worst case, not all of them bubble down. What about this node? This node worked like there was just one node in the top, right? Just one node. And how much work it did? If there are like in total n nodes, it did log n work. Why? Because the height of the tree is log n. So this one did log n amount of work. Okay, so if I put them in the equation, you see the one of the nodes, they did log n work. And then half of the nodes, they did just one step of work. 1/4 of the nodes did 2 steps of work. So the trick that we did this way is like most of the nodes did little work, where a small number of node did a lot of work. Okay, so if I take this equation, you see it's n over 2 into 1, n over 4 into 2, n over 8. This is the number of nodes, and how many, in the worst case, how many bubble downs each of them did? 3. Okay, so let's take this equation. It's going to be n over 2 into 1, n over 4 into 2, n over 8 into 3. This can be written as this. If I take n common, is 1 over 2 is 2, 2 over 2 square, 3 over 2 cube. So this can be written as this. This is the total amount of work that we are doing. So this is the total amount of work we are doing. Okay, so this is from level 1 to level log n. Okay, so this is the total amount of work. Now let's look at this equation. So this is the equation of geometric sum. You know how much is this? Up to infinity. This is 2. If you don't know, just go to this link and check the proof. Okay, so this is 2. Now you see this one actually is, okay, this is 2. Now tell me how much is this amount? This whole thing was 2. If I leave 1, the rest is 1, right? This is 1. So can I write 1 equals to half plus something like this, plus infinity? Okay, so now tell me, how much is this? Well, this whole thing was 1, right? I leave the half, so that rest is, and I say the rest is half. Can I say that? Okay. Next, sorry, I think it's not infinity. It should be 2 to the power 1 over 2 to the power infinity. Yeah, it's a very small number. Okay, so what about this? Well, there was half. I'm leaving 1/4. So this is going to be 1/4 or this, right? This is going to be now let's add all of these things up. If I add this portion, it will be 1 plus half plus 1 square, 1/2 square plus. Okay. Oh, sorry. Equals to, let's see, half plus 2 of these, right? Plus 3 of these, right? Yes. Now let's look at two things. This part, how does it look like? This looks like, or let's change colors. So this part looks like this. And this part can be written as summation of I over 2 to the power I, right? From 1 to, say, infinity. So can I say that this portion is actually less than, even less than this, because this one goes up to log n, this one goes up to infinity. So can I say this is less than this? Okay. Okay, so that there it is. And then this portion, what about this portion? This portion is 2, right? 2. So can I say that, let's write it down, 2 here and this. So 2 equals to this. So can I just write it down? 2 equals to, right? And this is even smaller than this. So can I say 2 is greater than, 2 is greater than log n I equals to 1 I to the power I. So total amount of work, can I just say work is, if I replace it by 2, right? So work is less than n into 2. That means total amount of work is order of 2n. Work is order of n. Okay? So if I go to back to my previous slide, you see the total amount of work is actually less than 2n. That means these Floyd's build heap runs in order of n time. This is a spectacular algorithm. It wasn't very intuitive at the beginning, because you see, like, we are building a tree, we are adding n nodes, right? And adding a node, it looks like it takes log n thing. The height of the tree is log n, but we just did it very cleverly. We made most of the nodes work less, and that way these algorithm now runs in order of n time. So Floyd's build heap algorithm runs in order of n time. Yeah, I hope you enjoyed this algorithm and you also understood how this algorithm works. You understood the calculation. If you haven't, please go through it one more time, and that's it. So build heap algorithm can be done in order of n time. Till next time, thanks for watching.